Today we're going to talk about how to convert data state to business events. So here's a brief overview. I'm going to go over the context, which is the problem that we're solving, the theory of how to solve it, and then the actual implementation of solving it. So a little background on the company. We do vehicle transport is one of our main products. So that's picking up a car or a truck or something, moving it from A to B. We do that in two different ways, loading them onto trucks, also physically driving them. ACERTUS also does other vehicle-related services, repairs, cleaning, storage, titling and registration, which is the legal side of operating a vehicle on the public roads. So what the business wants to do, of course, is grow and expand, get better, and we want to retain customers, grow our customer base. We want to be the easiest to do business with. And let me go back a second. So who are our customers, you may be wondering, and that's fleet management companies, manufacturers, dealerships, even individuals. So we have an order life cycle. So I'm going to focus on just one of those products since there's so many. So vehicle transport order lifecycle here is just really briefly summarized from order creation all the way from, we call it quote to cash, essentially. And so primarily so far we've focused on automating and event enabling this middle part of the lifecycle. So there's load board posting, carrier assignment, real-time status updates. So the first one of those and the last one of the middle ones are what I want to focus on. So the load board, it's essentially a platform for offering truckloads to third-party carriers. So we post an offer, hopefully they accept, they'll put in a request, we grant their request, assign that truckload to that carrier for a particular time period, and the happy path is the carrier goes, picks it up. That will be then we've hit the real-time status section here. So we'll provide real-time status updates internally and to our customers using near real-time events. So a little background on where we started, what we had to work with going into this. So ACERTUS was formed by merging together companies that had pre-existing resources. So they were operating, the business is flowing, we're making money, it's great. We want to expand and grow and give our customers what they want, but we don't want to disturb the existing business and change things too rapidly. So what we had to start with is relational databases that are being used to fulfill the orders, and then the business process is being executed. So I'll just jump right into the theory. Got to move pretty quickly, lightning session. So I'm going to define a couple terms I'm going to use here. So an entity is a uniquely identifiable object that has some collection of data that defines it. So like an order is an entity, a vehicle, a person, a place. A set is a collection of entities for which a logical predicate is true. So that's some statement that you can evaluate as true or false. So I have an example here. We have the universal set of all orders, and then we have two disjoint subsets, which are mutually exclusive subsets within orders. In this case, the example is en route and delivered. And so the next two definitions, so a state is a snapshot of an entity at some point in time. So it's the data properties that make up that entity at a point in time. And an event is a change in state, a particular change in state that something happened. So in this example here, the event is that the vehicle was picked up by a carrier. The state change is joining the set of en route. So here's a simplified architecture. So we have this black box here on the left, which is what the humans and microservices are using to fulfill the order, to actually execute the business processes. That state is maintained in a source of truth SQL database, in this case Postgres, From there, we have a Debezium CDC source connector that's change data capture, so we get all the CRUD operations, inserts, updates, deletes. And the state of the rows is then produced by Debezium into Kafka topics as messages. So from there, we have a large Kafka streams topology that reassembles the row states into order states. It puts it back together. Then we have a subsequent topology that derives the business events, produces back to Kafka. From there, it's available for webhooks being written back into a different Postgres optimized for searching table. It can also be available for analytics, for business intelligence. And so here's a little reasoning of why we need to do that. An order is broken apart. And in the relational database, we have some kind of parent entities. In this case, the primary parent entity is order component, which are then grouped into fully formed orders. And it has all this other data, these little individual tables that have, maybe just a handful of columns, maybe just 2 columns even, or 3. And so all those child entities, we need to group and aggregate carefully and join them to the order components. And we've got to do that for vehicle and for business partner. And business partner, again, is it could be the customer, it could be a location, something like that, a place, something relevant to the order, the carrier, of course. Those customers could be like fleet management companies, dealerships, et cetera. So there's usually several business partners associated with an order. So you can see there's a bunch of joins. And so we did that in Kafka Streams because it's very efficient. It can handle bulk updates done to the source database that someone might do. And it can do it in a performant manner without putting additional load on that source database. We're not going back and querying because we already have the data available in Kafka. So here is a really simplified set membership topology example. It's not optimized or anything. And I omitted some of the observability and transformations that would actually be there in production. So we have, let me go back to here. So we have a topology reassembling the orders. The completed orders come in as a stream of states that are then consumed by this type of topology. We apply predicates, and then we get another stream of states coming out. And we need to, an important part of this is detecting the set membership itself. So that's what is done in this, we do it in the processor API of Kafka Streams in this, on the right-hand side here. So we do a duplicate check. And this is needed because of the nature of Kafka Streams joins. It's essentially a fire hose of updates. And it may or may not be a set membership change. And so we need to suppress all those duplicates that are not a set membership change. And this is in a RocksDB key value store. And then also it's really important to maintain at least once processing guarantees. So that's where the metadata check comes in. If it's a reprocess, we'll forward it anyway, so that we'll have at least once processing. If it's just a duplicate and it's not a reprocess, it's dropped. So yeah, so the reprocess is important because if we forward and something happens to a producer exception or just something happens downstream, this wouldn't know about it. The state store, the events key value store would have already been updated. So yeah, it's important to have the reprocess check. Oh yeah, and of course RocksDB has great performance. It gives you locality of data. So it's right there. You have very, very fast queries without having a huge amount of I/O. It could be I/O just into memory. It could be a local disk or maybe a network disk like EFS if you're in AWS. So I'm going to quickly go through these analogs to SQL. So our load board, which remember is our platform for offering truckloads to carriers, that platform has a search capability. That search capability is implemented by querying a SQL table. So we take these events. We knew they were going to be used, eventually ending up in SQL, so we have the delete in there. So entering the set is an insert. predicates met that it's still in the set, but some detail change that doesn't actually affect set membership, but it does affect the downstream data that's important to the consumer. We do create an event for that. That's a SQL update. And then leaving the set, it's taken off the load board. It's assigned to a carrier, so we delete it, remove it to keep our SQL table small. Another example of a consumer is for webhooks. We're sending events to our customers. So they want to know when their order is being picked up or delivered or something like that. So that's a set membership change. That's entering the set of en route or entering the set of delivered. So we send them an HTTP request for that. If there's some property of the event that changed, they also usually want to know, so we send that as well. If it's leaving the set, we don't send anything because we don't need to. The sets are disjoint in the case of status. So it's entering another one, so we know, like, they don't need to know that it's no longer waiting. They want to know that it's on the road. Okay, so yeah, that's pretty much it, you guys. This worked out really well. We delivered the business value at pretty low cost. It's a good foundation for adding additional business events that we want to derive. We've done that already, adding some additional internal events. And we had to do really minimal customization of Kafka streams, just a couple custom processor API usages, a couple custom processors, and that was it. We're just using the default RocksDB. It's been great. Okay, thank you, everybody.